This is Miss Chang bringing to you session 5 of Rockville Chemistry. Hey, this is Miss Chang bringing to you session 5 of Rockville High's Chemistry. This is the week of May 4th to May 10th. Our topic this week is acids and bases. So our two learning objectives. First is learning about Earth's surface as a complex and dynamic set of interconnected systems, principally the geosphere, hydrosphere, atmosphere, and biosphere that interact over a wide range of temporal and spatial scales. All of Earth's processes are the result of energy flowing and matter cycling within all of these systems. And the next one is climate change can occur when certain parts of Earth systems are altered. Changes in the atmosphere due to human activity have increased carbon dioxide concentration and thus affect climate. So you're probably wondering, what does acid and bases have to do with the climate or the different spheres of Earth? If you guys remember that from middle school. So we need to kind of give you guys some background in chemistry before we get to these topics, because acids and bases go hand in hand with carbon dioxide. All right, so let's go ahead. We're going to talk about our key terms. Before our key terms, we talk about the assignments. So this week, there are 2 assignments. So please look at Google Classroom. They are due on the 10th this month. It's already May. Is that insane or what? So both of them are completion this week. So you're not going to get penalized if you get questions wrong, but please try to understand the material, try to learn it. So the first assignment is a Google form, just a basic practice questions on the properties of acids and bases. And then the second one is going to include a PhET simulation on the pH scale. We want you to answer the questions based on the PhET simulation. All right, so let's get into key terms. So the first key term we have is Arrhenius acid. So we want to define what acids are, and there's actually more than one definition of acids and bases. We also want to do Arrhenius base. Brønsted-Lowry acid, second definition for acids. Brønsted-Lowry base, second definition for base. Amphoteric, pH scale, indicator, and ocean acidification. So we've all heard these terms before, maybe not ocean acidification, but where do they come from? When you see something as a pH of 7, what does that actually mean? So, introduction. Acid and bases are all around us in the everyday products that we use. So whenever you eat citrus fruits, they have a sour taste because of citric acid. Your sour candies, such as Warheads or Sour Patch Kids, also are covered in citric acid. Bleaches, soaps, and other cleaning supplies are bases. So anything that's like slippery and bitter tends to be a base. And even in your genes, within your body, they contain acid. So DNA stands for deoxyribonucleic acid. That's a type of acid. Isn't that insane? So what exactly is an acid and base? And how is pH determined? That's our 2 main questions this week. So let's just introduce ourselves to some acids first. So acids are very important in chemistry and affect your daily life. The body needs acids and bases to function properly. So in your gut, you have a lot of acid. Your body produces hydrochloric acid, which is very caustic. If you were actually to touch it, it will start like eating away at your skin. However, your stomach has evolved to handle the strong acids that help break down the foods in your body. Vinegar, carbonated drinks, and foods all contain acids. So they tell you to brush your teeth before you go to bed, because the acids actually wear away at your teeth and erode it, and then it's going to lead to cavities and so on. So acids corrode at the calcium phosphate in your teeth. The electrolyte in the car battery is also an acid. So also in your phone, lithium-ion batteries, those contain acids. And most manufacturing processes use acids or bases. So they're very strong, they can dissolve things, they can clean things very well. You don't want to go overboard, but they're very good for industrial uses, and they're used to manufacture a lot of things. So, properties of acids. Acids have several common properties, so you do need to know these. So the first one, that all acids taste sour. So we're not going to tell you in the lab to go ahead and put your mouth on something and taste it, only if it's safe, but most acids are sour, which is funny, since I have a biology background, that your tongue has these channels, these receptors, and it detects how sour something is. So something that is more acidic is actually going to be more sour. And acids are also corrosive, so it can burn your skin. So if you ever felt the stinging of lemon juice on a cut, that's because of the acid. And then if it was stronger, it would hurt more. And acids react with indicators to produce predictable changes in color. So an indicator allows the person, the investigator, to have a general understanding of how acidic or how basic a substance is. And like bases, acids can conduct electricity. So bases, on the other hand, are typically not food. Although some foods, such as egg whites, as well as milk, are slightly basic. We don't actually eat all that many basic foods. Medicines like antacids are basic. So if you have acid reflux, a heartburn, that's probably because when you get older and you eat like crap, the acid starts coming up your esophagus and start burning. To counteract that, you want to eat an antacid, which will lower the discomfort of heartburn. And bases are typically important as cleaning materials. So nowadays with COVID, we're putting bleach everywhere. We're cleaning surfaces with bleach. They're really good at disinfecting, but you should not inject or inhale disinfectants. They're very bad for you. So properties of bases. All bases have several common properties. So they tend to feel slippery or soapy. So when you feel a bar of soap, that's because there's a lot of base in it. They have a bitter taste, so don't eat soap. If your mom ever puts soap in your mouth, then you know. And like acids, bases can also conduct electricity, and base changes the color of litmus indicator paper from red to blue. Acids go from blue to red. So you take blue litmus paper to test for acids, and red litmus paper to test bases. Definitions of acid and bases. The definition of what an acid is has changed over time as our understanding grew. The common themes in most acids: the element hydrogen. So acids have to have the element hydrogen. So if you hear about HCl, that is an acid. So water is always a product of a neutralization reaction when you mix acids and bases. And that water can also be an acid. So H2O can actually be an acid. So acids are characterized by forming a hydrogen ion when dissolved in water. So remember, when you take a substance and it dissolves in water, we call that aqueous, dissolved in water. So when you dissolve an acid in water, it produces the hydrogen ion. So it disassociates or breaks up in water. So for example, very common acid is hydrochloric acid. It's found in your stomach. When you dissolve it in water, the hydrogen and the chloride ions in HCl will dissociate, and then the H becomes the hydrogen ion. And then the Cl will be negatively charged, and then the hydrogen typically associates with water. It forms something we call the hydronium ion. So you might hear the term hydrogen ion being used interchangeably with the hydronium ion. They're not the same thing, but essentially what happens is that you could think of each dissociated hydrogen atom associating with water so that it turns into the hydronium ion. So in general, acids are substances that release hydrogen ions and produce hydrogen ions in water, H+. So the first definition of an acid is given by Swedish scientist Svante Arrhenius. I don't know how to pronounce that first name. So Arrhenius defined an acid in terms of hydrogen ions. So an Arrhenius acid produces hydrogen ions, which in water become the hydronium ions. The Arrhenius definition is limited because it only applies to solutions with water. So pretty much anything when dissolved in water produces the hydrogen ion, which will associate with water to produce hydronium ions. That is going to be an Arrhenius acid. So sometimes when talking about acids, the term protons, hydrogen, and hydrogen ion and hydronium ions are used together. A proton refers to a hydrogen ion. So thinking way back to the beginning of the year, hydrogen is the first element on the periodic table. It is exactly 1 proton, 0 neutrons, and in its neutral state on the periodic table, the atomic state, it has 1 electron. well, since it's an ion, it loses that one electron. So the only thing that a hydrogen ion will have is that positive proton. So we also call it a positive proton. And the hydronium ion is H plus in water. So here we go. We got HCl dissolving in water. And then HCl is our acid. And the proton H plus is going to be donated to water. So we get the hydronium ion, and chlorine will be by itself. So essentially this little H here comes and hangs out with this H2O to form H3O, which is positively charged. A definition of Arrhenius acids. So generally, Arrhenius acids produce hydrogen ions in water. Arrhenius acids, you got HCl to form H plus Cl minus. Another acid is nitric acid, which will dissolve to form hydrogen as well as nitrate ions. So essentially, anything with hydrogen in it that can dissociate in water, you could produce your hydrogen ions. You could call it Arrhenius acids, whereas Arrhenius bases produce hydroxide ions in water. So sodium hydroxide is a very common base, Arrhenius base. And then whenever you dissolve it in water, it forms our polyatomic ion, hydroxide. So you get the positive metal ion and then the hydroxide ion. Calcium hydroxide is another very strong base that dissolves to form our calcium ions and hydroxide ions. So the definition of an Arrhenius base is something that dissolves in water to form hydroxide ions. So our second definition is Brønsted-Lowry acids and bases. So while the Arrhenius definition was a good start at understanding acids and bases, it was limited because it's only thought of solutions in water. So not everything is dissolved in water. Sometimes chemists perform reactions in solutions that are not water or not aqueous. A new definition was needed. So that's where we came up with the Brønsted-Lowry definition. So Brønsted-Lowry theory defines acids and bases as either proton donors or proton acceptors. So this is more of a generous definition. So it comes from these two scientists that came up with it independently. So Johannes Brønsted as well as Thomas Lowry. So according to the theory, Brønsted-Lowry acids donate a proton. So you take a substance that is the acid, HCl, and it reacts with a base. It's going to dissociate and produce that hydrogen ion, which will therefore then react with will react with the base and then give the proton to the Brønsted-Lowry base. So there we go. Hydrogen is donated by HCl. It is accepted by the H2O, the proton acceptor. The Brønsted-Lowry theory defines acid and bases either proton donors or proton acceptors. So the Brønsted-Lowry base, instead of donating protons, will accept it. So H2O is our base here, and then actually no, H2O is not our base. So water is kind of tricky here. Water can be both an Brønsted-Lowry acid as well as a base. So water can dissociate as well, and it can donate its hydrogen ion to ammonia. So when this reaction happens, our Brønsted-Lowry acid here, H2O, will donate it to our Brønsted-Lowry base, ammonia, which will accept the hydrogen ion to form ammonium ions as well as hydroxide ion. So the formation of the ammonium ion, as the ammonia accepts a proton, and the formation of the hydroxide ion as water donates a proton. So here we go. Water, because of the fact that it's losing the hydrogen ion, will make it the Brønsted-Lowry acid. And because the ammonia gains a hydrogen ion, it suddenly becomes the base, Brønsted-Lowry base. Species that are able to act as either a Brønsted-Lowry acid or a Brønsted-Lowry base are known as being amphiprotic. So that's where water falls under that definition. So water is able to act as both a Brønsted-Lowry acid or a Brønsted-Lowry base. So in this situation, we have hydrogen reacting, and it's reacting with CH3 and H2, and it is donating a hydrogen ion to the species. So now CH3 NH3 plus, that base, Brønsted-Lowry base, accepts that hydrogen ion, and then we form OH after it donated that hydrogen ion. But it could also be a base. So here we have CH3COOH, H2O, where we have this species right here, CH3COOH. It loses its hydrogen because it is a Brønsted-Lowry acid, donates it to water, and water accepting the hydrogen ion will suddenly become H3O because it gained a hydrogen ion. So water is an amphiprotic substance, something that can act as both an acid and base. So an acid and a base that differ only in a proton is called a conjugate acid and base pairs. So this is very important for our theory on ocean acidification. So essentially, what happens? We're going to use this example right here: ammonia with water to form ammonium and hydroxide. In the forward reaction, the ammonium ion is the conjugate acid of the base NH3. So NH3, whenever it gains that hydrogen ion, will suddenly become the conjugate acid because it gained that hydrogen ion. So and the OH ion will become the conjugate base of the acid H2O. So acids, when it donates the ions, the remaining OH is going to be the conjugate base. And the NH3, when it gains that ion, the base will become a conjugate acid. So in the reverse reaction, NH3 is the conjugate base of the acid NH4. So if we read this reaction backwards, NH4 can dissociate and donate an ion to H2O. Our acid right here will turn into a conjugate base species right here. NH3 is the conjugate base, and hydroxide, because it is accepting a hydrogen ion, that the base in the reverse reaction will become our conjugate acid in the reverse reaction for our product. So here, we want to do a little bit of practice. You're going to be able to do this on your practice quiz as well. Identify the acid, the base, the conjugate acid, and the conjugate base. So right here, ammonium ion reacting with water forms ammonia and H3O, hydronium ions. What is the conjugate acid? What is the conjugate base? So just look at that for now. Which one is donating a hydrogen ion? Which one's accepting a hydrogen ion? And therefore, what is the conjugate acid? What is the conjugate base? It's helpful to identify what are our conjugate pairs. So for the first reaction, because NH4 is losing a whole hydrogen ion, we could assume that NH4 is the acid donating its proton to H2O. So if NH4 is the acid, the conjugate base must be NH3. And because H2O is accepting the hydrogen, that falls under the definition of a base. So therefore H2O is the base, that H3O will be the conjugate acid. So acid, base, conjugate base, and conjugate acid. So for our next reaction down here, we got HCOOH plus CN reacts to form HCOO that's negatively charged and HCN. So acids, once again, they donate a hydrogen. Which one seems to lose a hydrogen? Are HCOOH or CN? And then for a base, which one's accepting the hydrogen? So looking here. So it looks like our HCOOH is our acid because it's losing the hydrogen. Therefore, the CN is the base. And because HCOOH lost the hydrogen, the pair, the rest of it will be the conjugate base. And HCN, therefore, will be the conjugate acid. One more. So this is the reaction that we're going to focus on next week. We have water reacting with H2CO3. That's carbonic acid to form hydronium ion, and it looks like a hydrogen. Actually, don't know the name of this. It's a carbonic acid, so this might be carbonous acid right here, HCO3. So which one donated the hydrogen? Is it H2O or H2CO3? So seeing that our H2O gained a hydrogen, I would say that the H2O is the base. That therefore the H2CO3, our carbonic acid, will be the acid. So thinking about our conjugate pairs, H2O therefore will form our conjugate acid, H3O plus, and H2CO3, our acid, will form our conjugate base, HCO3 is negatively charged. And then right here we have one more reaction. We have HCO3 plus water reacting to form our hydronium ion, H3O plus CO2. Which one lost the proton? Is it HCO3, negatively charged, or H2O? So seeing that our H2O gains an electron, not electrons, my bad, a proton to form hydronium ions, that it must be our base. Therefore, HCO3 must have been our acid, and it donated a hydrogen to H2O. So HCO3 is the acid, H2O is the base. Therefore, that makes the pair H2O turn into our conjugate acid, H3O, sorry. And then HCO3, having donated its hydrogen ion, becomes our conjugate base. So this is what happens during ocean acidification, which we'll go more into next week. So essentially what happens is that CO2 in the atmosphere, it can only go so far. It doesn't all stick in the atmosphere. That some of that CO2 can actually dissolve in water. So when CO2 dissolves in water, it will react with water to form carbonic acids. Look at this here. We have one carbon here, two oxygens here, and another oxygen in water, and two hydrogens. So when they all combine together, it forms carbonic acid. And then whenever carbonic acid disassociates in water, it's going to form bicarbonate ion, which is a negatively charged species, as well as the hydrogen ion. And remember, if it forms hydrogen ions in water, it's an acid. And then that hydrogen ion can also react with carbonate to form bicarbonate. So when there's more CO2 in the atmosphere, more CO2 is going to be dissolved in the water. If more CO2 is dissolved in the water, you form more carbonic acid. Therefore, more hydrogen ions are going to be dissolved in the water, and it's going to lower the pH. So we want to talk about what does that mean, lowering the pH, in the next few slides. So pH scale, you've probably seen this before. It ranges from 0 to 14, with 7 in the middle corresponding to neutral, whereas anything less than 7 will be acidic, whereas anything higher than 7 is alkaline. So our FET today is going to focus on the pH scale. So the pH scale is used to distinguish between acid, neutral, and basic solutions. The P in pH comes from the German word potens and Danish word potenis, which both mean power, and H means hydrogen. So the power of hydrogen. So essentially, the pH scale allows you to identify what's the concentration of hydrogen ions in a solution. So we have the pH scale right here. So the strongest on our scale is number 1 for our acids. Gastric acid is the most acidic on the scale, followed by lemon juice, then apple juice and tomato juice, then black coffee, milk, and then water is neutral. 7 is neutral, meaning that it's neither acidic or basic. And then towards the right, above 7, we got basic substances. So the further towards the right we go, the more basic it is, or we could say alkaline, same word, same meaning. So eggs are slightly basic, followed by baking soda, and then hand soap, ammonia solution, bleach, and then concentrated solutions of alkali. So we have bleach here. It's a very fun topic to talk about these last 2 weeks, that the further towards the right or further to the left, so further away from neutral you get, the more caustic a substance is. Caustic means that it can burn and eat away at skin as well as clothing. So when we tell you not to drink or inject bleach, there's a reason why. So the pH of a solution is the measurement of the amount of hydrogen ions, which is denoted by H plus within these square brackets. The square brackets means concentration. So remember we talked about molarity as molality, as in moles per liter or moles per kilogram. We want to talk about the concentration of hydrogen ions to denote how acidic something is or how basic something is. So the greater the hydrogen concentration is, the lower the pH is, the more acidic the solution is. So to indicate pH, a scale ranging from 0 to 14 has been devised. Solutions with a pH lower than 7 is described as acidic, as I mentioned before, and anything higher than 7 is basic. One way to determine pH is by using a universal indicator paper. So the universal indicator paper looks like this right here. We tend to use it in labs, and it's rainbow colored. So this paper undergoes a color change in the presence of H3O ions, hydronium ions, and hydroxide ions in solution. The final color of the pH paper is matched with colors in the chart to find the pH. So it's a rough indicator. It doesn't tell you exactly how many hydrogen ions are in the solution, but it gives you an approximate ball feel. Whereas a pH probe is another tool to determine the pH of a solution. This one's much more accurate. So the pH meters typically has a range of 4 to 6.86, and it works between the temperatures of 0 to 50 degrees Celsius, and the resolution is to 0.1 pH. That makes it a lot more accurate than within the ones place, where it's 1, 2, 3, 4. This is by 0.1, so you can get 1.1, 1.2. So there's much more precise for scientific calculations. This meter is operated by immersing the electrodes in the solution to be tested and reading the dial. So you stick it into the solution, and then the probe will read what the pH will be. So to summarize this, acids can form hydrogen or hydronium ions whenever they ionize in solution. So when you dissolve in water, they dissociate, produce hydrogen ions, which therefore then associate with water to form hydronium ions. And bases can form hydroxide ions when they ionize. Arrhenius acids produce the hydrogen ion, whereas Arrhenius bases produces the hydroxide ion. A Brønsted-Lowry acid is a substance that donates hydrogen ions, whereas a Brønsted-Lowry base is a substance that accepts hydrogen ions. Conjugate pairs differ only by a hydrogen ion, and the pH is measured by how many hydrogen ions are present. An acid is a substance with a pH lower than 7, and a base is a substance with a pH greater than 7. And a pH of 7 is neutral. So why is understanding acids important? So increased CO2 in the atmosphere produces more carbonic acid. So H2CO3, the carbonic acid, whenever CO2 dissolves in the water, will form bicarbonate and hydrogen ions. Got more free hydrogen ions, it's going to actually react with the calcium carbonate that is found inside the minerals of ocean shells, as well as coral reefs and so on. Carbonic, the calcium carbonate that's found in seashells as well as corals, actually what's found on the enamel of our teeth. So remember when I said earlier, when you drink soda or anything acidic, that it eats away at your teeth and causes cavity? Well, that's the same phenomenon happening in the ocean. The more hydrogen ions you have, it's going to start eating away at the shells of animals. So we're kind of messing up the animals here in the coral reefs. And then coral reefs are dying off in massive numbers across the world because of ocean acidification. So here are a few resources just in case you want to look closer into this topic. So a video to understand how increased CO2 in the atmosphere causes changes in the pH of the oceans. If you want to read a little more about acids and bases, we got a CK12 reading here. And Chemistry 1101, Introductions to Acid, Bases, and Salts. And Chemistry 1102, Indicators in the pH scale. Thank you for listening. Please make sure you do the 2 assignments this week. There are 2 separate Google Forms of both completion. One is the Google form on the practice problems for the properties of acids and bases, and the second one is our acid and bases effect. Thank you for listening.